actually based here in Zug, and we actually have a small office in this with CV Labs, so it's really great to be here today and to be presenting on our home turf for a change. I'm not alone. I'm also joined today by Philipp Kant, who is the Director of Formal Methods from IOHK, as well as Alexander Diemans and Nicholas Clark, who are also co-developers on the project. And I think what I'll do today is just give you a very sort of brief overview of the history of the project, Cardano, the philosophy behind Cardano in this project, and then I'll hand over to Philipp, who's going to talk in a lot more detail about the actual protocol, Orboss, and also very importantly the sort of development methodology that we're using to build Cardano, which is a sort of a fundamental part of the project. Okay, so how did it all come about? Cardano is a project which started in 2015. It has its origins in Japan, and a group of people came together to launch the project, including Ken Kodama, Charles Hoskinson, and Jeremy Wood. And I think some of you will be familiar with Charles. He's very well known in the space. He's a veteran in the space, a mathematician, an academic. And both Charles and Jeremy were also involved in the early days of Ethereum. I think it's important to note that this was always conceived as a collaborative project from the very beginning. And so there's three entities which came together to realize this goal, to realize Cardano. And that is the Cardano Foundation, IOHK, and Emergo. And I'll just quickly give you a brief overview of those three organizations. So Emergo is another company with Japanese roots. I think they have offices in Tokyo, Singapore, and New York as well. They're essentially the investment arm of our space, so they're like the consensus of our ecosystem. And Emergo it provides capital and advisory services for startups and businesses that are looking to build on the platform. And actually we were not expecting to have anyone from Emergo today, but we had a surprise visit from Manmeet Singh, who is the Chief Investment Officer of Emergo. So thanks for coming, Manmeet, and if any of you guys have questions later, you can speak to Manmeet as well. I'm sure he's really willing to answer any questions. So maybe another thing worth mentioning about Emergo, they also do software development for the project, which supports and sustains the ecosystem. The other organization is IOHK. They're a blockchain research and engineering company founded by Charles Hoskinson and Jeremy Wood, who I've mentioned earlier. And they are the technical lead for the project, so they're actually building and developing the protocol. And then the third organization is the Cardano Foundation. We're a non-profit based here in Zug. We're very active in community development, so we grow the ecosystem through community outreach. We have community managers in Japan, in South Korea, in China, in Holland, in the UK as well, and we're always looking to expand the team as well. So we're very active in terms of community development. We facilitate partnerships which sustain and support the ecosystem and which drive adoption of the protocol. And lastly, we also engage with regulators and policymakers to advance the discussion around legislation, standards, and so on. So I'm going to go, what is Cardano? I'm going to go through this very briefly. Philipp's going to talk about this in much more detail. But it's an open source public blockchain smart contract platform. We aim to be a global financial operating system for the developing world. We're a proof of stake. We use a proof of stake consensus mechanism called Orboss. And Orboss is actually a family of consensus mechanisms. And this Orboss was developed by IOHK's chief scientist, Aggelos Kaisis. Cardano uses a layered architecture, which means we have separation of concerns between accounting and computation. And we're also tackling these key issues of scalability, interoperability, and sustainability. And I think some of you may have also attended some of the other talks that happened throughout last week, throughout the series, and I think it's clear that these are issues which are being tackled by many projects, but I think it's fair to say that Cardano is really addressing each of these issues in a comprehensive way. Another really sort of defining aspect of the project is the development methodology. So more and more there's this realization that if we're going to build these protocols that are going to sustain millions or billions of dollars worth of value, if they're going to secure our identities, if they're going to enable voting, if they're going to enable transparent voting mechanisms, then we really need to embrace the highest software development standards possible. And so how do we do this? Well, all of the academic research that IOHK does into building the protocols goes through some form of peer review, and we embrace formal methods and functional programming as a way to sort of ensure that the ideas that are reflected in these academic papers, which go through peer review, to ensure that the implementations are actually correct and equivalent. So it's something that Philipp will talk about in more detail as well. And yeah, while it's important that we innovate, and we must innovate, we mustn't do so at the expense of security. And I think more and more projects are adopting this approach. And I think it would be fair to say that IOHK IOHK are really an industry leader, at least in the cryptocurrency space, in terms of pioneering these methodologies. And lastly, I just want to mention community. Community is really important for us, for our project. I mentioned in one of the earlier slides that the project was always conceived as a collaborative effort from the very beginning. And there was always this idea from the very beginning that there shouldn't be a single group of actors that are in control of the development of the protocol. And so the long-term vision for the project is always one where the community themselves will govern the project and do so democratically via the stakeholders themselves through a democratic mechanism will be able to make decisions on how the protocol moves forward. And so transparency is really important for this project. So we sort of aspire to the highest levels of transparency that we can. And I think some of you who are familiar with Cardano and follow the project will see that our community managers, Charles Hoskinson in particular as well, are regularly updating the community about the status of the project. It's the good, the bad, and the ugly. But it's all about transparency. We want to instill a sense of ownership in our community, because the long-term vision is that this will be a community-led project. So that's it from my side. That's just the quick overview. And I'm going to hand over to Philipp, who will talk a lot more about the protocol in detail. On this side.
Okay, so thanks for inviting me here to speak about Cardano, and I'm going to talk about several aspects of the thing. I'm going to talk about the proof-of-stake mechanism itself that's underlying Cardano. What's the proof-of-stake? Why do you want to use it, and what's the Orboss protocol in particular that's underlying the Cardano system? Then I have a section on how we work in order to ensure that what the researchers come up with and what they envision, what the intent to have actually ends up in the running code. So how we make sure that what's in the papers ends up in the system that we can all use. Then I'm going to talk a bit about the smart contracts languages that we have developed. And I'll also just list a few of the future developments that we still have in stock for Cardano. So first of all, proof of stake. Well, what's it for, and why would you want to use it? And let me take a step back for how we used to do money. And I mean the first thing that we did was just exchanging physical tokens, and that's quite practical. You don't have to, you can't forge, I mean you can forge money of course, but you can't claim that you have something that you don't have, and at the moment you give it to somebody, you have transferred the ownership. But the thing about it is that once you start doing that at a distance, it gets really inconvenient. You don't want to send this via mail or anything. It gets slow and inconvenient and insecure. So the next thing that you can do is just to use a written ledger instead. And for that you typically use a central authority that keeps that ledger, and then everybody who wants to send some money just tells that authority to perform a transaction on their behalf. And that works quite well as long as everybody has trust in that party. Because of course if there's only one copy of the ledger, then the person who owns that ledger and who has control of the ledger can rearrange it, can forge it, or could also just refuse to send transactions that somebody sends there, and then they can't use their money if the bank does that. So the question is, what can we do about that? Can we do something that doesn't require trust in one central party? And the answer is, well, we decentralize the ledger. Instead of one computer that holds the ledger, we have a multitude of computers, and everybody has a copy, and everybody keeps the copy in sync, and then everything works well. But of course, it's more complicated than that, because you need to have consensus on that. As soon as those computers start disagreeing on what the state of the ledger is, then you need to have some mechanism on making them agree again. So let's take a look at how you can share the control over a ledger between different parties. And so in this simple example, you just have 3 people. They're still in one room. They have one ledger, and these colored bars here, that are transactions that somebody sent to them and once entered into the ledger. And so what you can do is just take in turns and then move the ledger around from person to person, and they check whether that transaction is valid with the current ledger state. And if it doesn't fit with the current state of the ledger, then they just discard it. Otherwise, they pass on the ledger, and so on and so forth. That's nice, but that only works if those people are close to each other, because you don't want to send that ledger that you have around, because then it gets slow and dangerous again. And also, this assumes kind of that there are those 3 people and not more than 3 people, and you have to select those 3 people, and then everybody has to select the entity controlling these 3 people. So the next step is then doing that in a distributed setting. And what you want to do there is that you don't send the whole ledger around, you just send individual pages around. So you have basically the state of the ledger is the state of all the previous pages. And whenever somebody is the leader, then they construct a new page and link it to the last one that they've seen, and then send it around to everybody else. And then you basically have a blockchain. So you have these pages that called blocks, and then you link them together, and then that's nice. And sometimes the person whose turn it is to create the next page might not have seen the last page yet. So then they'll create something that links to something back in the future. And the way that you resolve that is then that the next person whose turn it is just decides to pick either that one or the other one. And then all the other ones will build upon the longest chain, and then you get consensus in that way. And so that way you have transactions that have just been entered into the last page, they might get reverted, but after a time, if there's enough blocks on top of it, then it's reasonable to expect that they will not be reverted anymore. Of course, that doesn't really solve that doesn't yet solve the problem of permissionlessness. So right now we still need a fixed set of people who send these pages around, and for that we have these different kind of protocols like proof of work and proof of stake and so forth. Now, what's the problem with just allowing anybody to join and then just taking regular turns in some way? Well, if you do that and you don't have anybody who controls who is a member of that set, and nobody checks like passports or anything, then this person up here could just pretend to be a 1,000th person or 2,000 persons, and then you have what's called a civil attack. And if you then take turns, then this person up here would have several turns in a row, and then they could just manipulate the ledger, and that's not something that you want. And so the proof of work solution to that is that instead of checking identities, you require that everybody who joins the system as a computer, and then they basically do a race each round in computing some arbitrary mathematical puzzle, some hashing problem, And then the first one who gets that just gets the right to produce the next page in the ledger. And with that system, you can then prove that as long as the majority of the hashing power is in the hands of honest parties who don't try to neglect some transactions and who don't try to revert some transactions, then everything works fine. Then you have the liveness property that if you send a transaction to the ledger, it will get into it at some point, and you also have the persistence property that it won't vanish again after it becomes stable. Of course, the problem with that is, as long as everybody just uses their own computer, it's a fair thing, and it's basically still like taking turns with a bit of randomization, because it's not strictly taking turns, but everybody will produce about the same number of blocks. But then as soon as you give incentives to produce many of these blocks in terms of monetary rewards, then somebody might think about not using just one computer, but a rank of computers, and then everybody else will do that as well, and then you have this arms race, and that's very bad, because if you look at Bitcoin, then you have the power consumption of a small country just for quite a small system that does something like 5 to 10 transactions per second, which is kind of ridiculous. So we need to do something about that. It's not productive. It's just an arms race and producing heat and entropy for solving this problem, which we should be able to solve easier, right? And the way that we can solve this easier is with proof of stake. So in essence, this proof of work, this permanent race of solving this mathematical puzzle is something like a lottery, and each unit of CPU power that you put into it gets you a ticket in that lottery, and then if you win it, you get to produce the next block. Now, instead of using CPU power for that, we could use another bounded resource that's in the system, and that's just the amount of money that you have within the system, and that's your stake in the system. And so, if you just do a lottery based on the amount of stake that anybody has for producing the next block, then that's called proof of stake. So that's nice, right? So why isn't everybody doing this since ages ago? Well, there's two problems with that. One is that it's actually quite challenging to do it correctly. If you look at it from an abstract point of view, then you're trying to secure the ledger with the system, and you need to have information on that ledger in order to run that system. So it's a bit self-referential, and that leads to a number of attacks that you can do there. And furthermore, in proof of work, you have like producing a single block takes you extra work. And in proof of stake, you can just, as long as you win the lottery, you can produce any block you want. And you could, in particular, produce many blocks and have them compete against each other. And that leads to a number of attacks that you can do on a proof of stake system if you don't design them in a way that hardens them against these attacks. So one category of attack is called the grinding attack. And the idea there is that this lottery that was implicit in the proof of work setting is explicit in the proof of stake system. So you have a random number generator, and you have stake distribution, and then those two things, they determine whose turn it will be to produce blocks for the future. And if you have either any influence on the random number generator itself, or if you know the state of the random number generator, and can then manipulate the way that your stake is organized in the system, then you could kind of do that in a way that maximizes your chances of getting elected. And so by basically simulating different futures for the blockchain and then just acting in a way that tries to push it in the right direction, you could trade some CPU power for effectively stake. And that's something that you don't want to do in a proof of stake system. The other thing is called long-range attack, and there the idea is that since it's cheap to produce blocks, as long as you are elected, you could try to do something like if you have a history of the chain that goes like that, you could, and you have some stake initially, then you could just ignore all other blocks but the ones that you can produce, and then hope that after some time, either by rewards that you get or anything else, so after a period of a very sparse chain, you have control over the majority of stake, and then you can just produce the future. And for somebody who doesn't know which is the original history, then they have to basically be able to decide which one is the forged one, where you cheated, and which one is the original one. So that's called long-range attack. And then there's also the what's called a nothing at stake attack. And there the idea is, if you already have a fork in the system, and you are a miner in a proof of work system, then you would have to decide to either create a block that fits on here, or one that fits on there. Because if you try to produce a block for both, then you would have to divert your computational resources to that, and you would likely not win anything. But in a proof of stake system, in principle, you could just add a block here, and you could also add a block here, and then you would basically bet on both chains, and whichever chain gets chosen, then you would get your rewards for that block. But in doing so, of course, you prolong that fork, and you don't help resolving that. And that's something that's bad for the system health. So those are a class of attacks that people have thought about performing on proof of stake systems, and that you have to be prepared against. And then, of course, the other thing, why didn't Bitcoin switch to that? That's just the question of getting consensus among all the Bitcoin miners is difficult. And in particular, telling them, hey, we want to get rid of miners entirely is something that's a hard sell for people who have invested lots of money on mining hardware. So in Cardano, we use the Orboss protocol, which, so the name comes from the Greek mythology. It's a snake that's eating its own tail, and in a minute you'll see why that name was chosen. And it is the first provably secure proof of stake protocol that doesn't have issues with those problems that I mentioned. And that guarantees that as long as the majority of stakeholders, so the majority of stakeholders weighted by their stake, performs honestly, performs according to the protocol, then you have these persistence and liveness guarantees, and you can use that for a secure ledger. How does it work? Okay. The basis for that is, of course, the stake distribution. So in this simple example, again, we have three actors. You have red, blue, and green. And then you have, in the beginning, you have some stake distribution, so it's more or less even here. And then based on that stake distribution and some given random seed, you can just divide the passage of time into discrete slots. And for each slot, you randomly chose one of their stakeholders by just doing that proportional to the stake that they have. And then you end up with something like that. And then you can look what happens as time passes. You produce a red block, you produce a blue block, or the green node produces a block, and so forth. And then time passes, and time passes, and time passes. And during that time, we still assume that the stake basically didn't change too much over that period of time. But of course, over some time, the stake distribution will change. So at some point, we have to take a new snapshot of the stake distribution. And that's somewhere around here. We basically look at all the transactions that have entered into the ledger at that point. And then we look what the new stake distribution is. And then in this example here, the blue player has spent something and distributed to the red and the green ones. And so we keep that snapshot in mind. The next thing that we do is that over the course of the next couple of slots, we produce some randomness. And that has to be done in a way that nobody just dictates the randomness, but that there's some influence from everybody. So you could do that by sampling something from the chain that is hard to manipulate. Or what's done in the classic Orboss paper is that basically a number of people perform some coin tossing, roll some dice, and produce some random numbers. And then they don't immediately reveal those numbers, but they reveal something with which, when they later on reveal their result, you can verify that that was indeed the result that you committed to. So you post a commitment to the chain, and later on, seeing that commitment and your result of the dice, anybody can see that you didn't lie in the beginning. And in that way, you prevent that basically the last one to roll their dice can lie and then just set the randomness to whatever they want. And that's what you do then during the later stages of the epoch. And then once the circle is complete, you can, based on the stake distribution and the randomness that has been generated during that epoch, you can create the slot leader schedule for the next epoch. And at that point, basically, the snake eats its own tail, and that's why the protocol is called Orboss. You can immediately see, just by the order in which things happen, that this grinding attack, where you try to manipulate the stake distribution reacting to the randomness generator, is not possible here, because you take a snapshot of the stake distribution, and afterwards the randomness is generated. So if you do manipulate the stake distribution after here, it doesn't really matter, because during the next epoch we just use these assumed more or less static stake that we did a snapshot of here. So you can't do this blinding attack. What about these other attacks? Well, for the long-range attack, there's a modification of the chain selection rule. So the most naive thing that you could do would be just to take the longest chain that is presented to you whenever you're presented with multiple chains. Now, in this case, this wouldn't be too good, because after a long period of time, so imagine the system has been running for a couple of years, and then somebody starts doing this long-range attack, and you just start joining the network, and you would see those two chains, and you couldn't really determine, and you would just pick the longest one, then you would take this forged one. So there's two things that you can do to mitigate that. One is to not accept blocks from the future, because that would make it very easy to just produce a longer chain there. And then to mitigate this true long-range attack, you can not only look at the length of the chain, but also look at the density of the chain in between, because in order to do that long-range attack, you have to have a period in the beginning where the chain is sparser than the true chain. And if you just basically look at the sparsity of the chain in the past, in addition to the length of the chain, then you can prevent this long-range attack. And that's also something that our researchers have formalized. It's called the Genesis rule, because this first block is called the Genesis block. And so that allows you to get the true chain from the Genesis block without any information without trusting information from somebody who's been there all the time. So that's also something that we can check. What about the nothing at stake attack? So remember, we have the situation where we already have a fork that is just there because either somebody was malicious or somebody just didn't get the last block in time. And then as the next slot leader, you have the opportunity of either picking one of those blocks, one of those forks, and adding a block to it, which is the thing that is honest, which is expected of you. Or you could, of course, you could do nothing, which would be, which doesn't make sense. Or you could bet on both forks, basically, and add a block to both, and then play it safe and win and get your rewards for that block, no matter which one gets continued. The thing with that is, of course, if you produce a block for both of those blocks will have your signature. And so everybody can see that you cheated, because producing two blocks for the same slot is something that's not allowed by the protocol. That's dishonest behavior, it's attacking the system. And if you want to do anything with those blocks, you have to send them around, and then everybody will see, even though only one of them will end up on the eventual chain, but everybody can see that you have been dishonest. So what's at stake here is really your reputation. And if you see an actor who behaves in this open aggressive behavior, in this open malicious behavior, then you will just ignore them and just not accept anything from them in the future, because they are trying to attack the system, and you know that. And so there's quite a lot at stake here. It's basically your ability to continue in the game with your honest actors. So that's also something that we can solve. And that's basically a brief introduction to how the Orboss protocol works, and also what it achieves, namely that it's a protocol that is provably secure, uses proof of stake. And so if you read the paper, then there's analyses and proofs that basically guarantee that as long as the majority of stake is in honest hands, that means players who behave according to the protocol, then you have this liveness and persistence property. Right. Now let's get to the next section of the talk. So in case you missed the train of thought in the past, this is a new opportunity to get going again. This is about how do we ensure that what the researchers wrote in the paper actually ends up in the code. And for that, let's take a step back and look at all the things that can go wrong in the space. And the first one is flawed protocol design. If your protocol just isn't sound, then no matter what you do, you'll end up screwed. But luckily, the proofs have gone through peer review, so that doesn't bother us too much. Of course, then you can have an incorrect implementation of the design. Just because the paper says this is correct, if you start implementing that, you can still make mistakes. So you have to prevent that somehow. And there are, you can misunderstand the design when you start. There's typical software mistakes, like off-by-one errors, lots of things that just happen in software. You can also just roll your own cryptography, have some nice ideas how to improve the cryptography, and that can go horribly wrong, so you shouldn't do that. You could just have the software performance be bad enough that it breaks down under load, and that as soon as people pick up and use it, or even launch denial of service attacks deliberately, that the thing breaks down. And then of course there's stuff like economic attacks. If the fee structure isn't right, or then you can the system, even though it's working technically, you can still have it become dysfunctional. But since we now have this nice protocol, let's focus in the next part of the talk about how do we avoid making incorrect implementations or those typical mistakes that you make when you're doing software. And so if you just do industry standard practices, then unfortunately that doesn't give you very good software. I mean, if you look at all the devices that you have and you look at how often you install security updates, then it's kind of obvious that even big companies regularly make mistakes, and they are critical, and they are security relevant, and you have to update your software in order to patch them. But if you do this in a cryptocurrency where you can't roll back history, then just having an exploit there for a short amount of time just allows somebody to steal all the money, and then it's gone. And this happens regularly, and I mean, I'm not really that firm in the history of blockchain applications, but there's names floating around of incidents where this has happened, where just some contract was written badly, or some, and then people can steal money, and then it's gone. So you really don't want to just use industry standard development methodology, because that doesn't prevent bugs from entering your system. What can we do to assure that our software is correct? Well, there's the one approach, which is basically industry standard, which is the faith-based assurance, which is not really assuring you of anything, which is saying, okay, I just hire good people and they'll do the right thing, and then I'm confident that they won't make mistakes. But unfortunately, everybody makes mistakes. So this is not really a way to get assurance that your software is correct. What I'm going to talk about is evidence-based assurance. And when I say evidence, I mean that it should be objective evidence, because having faith in the top-notch engineers, that is not something that's objective. That's just something that you have after reading their CVs, or because you know them and you got drunk with them or whatever. And so this evidence that we want to have should be objective, so that anybody could go on and look at the evidence and review it and convince themselves that indeed this is evidence that the system is correct. And this evidence should be generated by the process in which we develop software. So how do we do that? Well, if we want to have this done in an objective way, we have to do this in a formal way, where we have formal specifications that say concisely and precisely and unambiguously what the system is supposed to, because only if you have that can you then basically give something like a proof or an argument for that the system actually does that. And in order for them to be concise, precise, and unambiguous, well, the best thing to formulate them in is mathematical notation, because that's what it was invented for, and that's what we've been using it for a couple of thousand years. Then once you have that specification, you need evidence that the implementation actually does what the specification says. And there are different levels in which you can do that. You can make a mathematical proof, and that's basically the best thing that you can do. And if that mathematical proof is also machine checkable, then you have reached nirvana. But unfortunately, that's very slow, and because it's slow and takes time and work, it's also expensive. So you can't do it all the time if you want to get something out the door. The next best thing that you can do is to produce evidence by testing. And that can actually be quite good, and it's also much quicker and much cheaper. And so what you do basically depends on how long you are willing to wait, how much money you are going to invest, and what level of assurance you want to have. So there are some trade-offs in choosing that. You must look at the system and look at which parts are really critical. If something goes wrong there, then you're basically screwed. And then you can make a choice from component to component of what you want to do there. And basically, as a rule of thumb, the higher the quality of the evidence you want to have, the more effort you have to put in and the more time you have to put in. And so this is, I mean, the proof is the one extreme, testing is basically the next best thing that you can do if you're doing it right and if your tests are meaningful. And so for Cardano, for the next implementation of Cardano, for the Shelly, we have focused on the ledger rules, and for the ledger rules we do something that is a semi-formal approach that I'll sketch here later on. So for other things like the way that the nodes communicate with each other, we have used more of a prototyping and peer reviewing approach. But the ledger is basically, that's what holds your value. So there we want to make sure that everything is really correct. And it's also, it doesn't only hold the value, but the value through the proof of stake algorithm also gives you the security of the overall system. So we want to make sure that the ledger is really correct. So what do we want to have there? We want to have a chain of evidence from the intent, which is expressed in the papers, to the working code. And the starting point are the papers by the researchers. And then we need to translate that into these formal specifications that are precise, concise, and unambiguous. And then we want to design the software in such a way that it's easy to compare them against those specifications. And then, if we can do that, then we have a link from the specifications to the code, and we'll use systematic randomized testing for that. So let me sketch how this looks. We have different stages here and different people who are involved in that. We start with a scientific paper, and then we have other researchers to read those papers and basically say, yes, this is good, and I'm convinced that this is indeed solid, and I didn't find any mistakes there, and this is good. Then the paper is checked, and we can go to the next stage, which is writing those specs. And then the specs are something that you have to look at, and then basically you have to have people who understand both the paper and the specs, and they have to be able to basically say, yes, this is indeed what was expressed in the paper. The intent of the paper is captured in those specs. The next step is then an executable specification that is not only understood by the people involved, but also by the computer. So the computer can run this and can check that it's self-consistent. It can't check the intent, of course, but it can check that it's consistent, and it can run it. And this then also gives you a basis for testing the actual implementation, because the executable specification can basically produce results that you can compare with the actual implementation later on. And I'll go into detail on each of those steps. So peer review, that's basically, that's experts looking at documents. The next thing, looking at those formal specs. So how do they even look like? So when you start writing them, it's not a process of just reading the paper and then writing down what's in there. It's more an iterative thing where you write down something, you think about it, you give it to your peers, they ask questions, and then you go over this, and then finally you end up with something that looks like this, which is extremely nice. So who of you can read this? Who of you is familiar with that syntax? Okay, very good, Nick. Okay, so let me explain to you how this goes, because it's really, it looks a bit, I mean, it might look a bit frightening, but it's a very precise and concise notation of what's going on in the ledger. So what this describes is the transition that the system undertakes when you add a new transaction to the ledger. And in order to understand that, you have to know a bit about how accounting in Bitcoin works, with just this UTXO model. I'm not sure how familiar everybody is with that. So the idea is that these red things, that you have some piles of money basically lying around, and then each transaction can take a number of money piles as inputs, and then it can produce new piles of money as outputs. And then all of those outputs that are not connected to a new transaction yet, those are called the unspent transaction outputs, because they are outputs of previous transactions and they're not spent yet. So this is basically all the money in the system. And now when you add a new transaction to the ledger, then you take some of those outputs and you have to remove them from the UTXO set. So UTXO is just the abbreviation for unspent transaction outputs. And you have some new outputs that you have to add to that. And that's precisely what is written here. So you have the UTXO makes a transition. The rule is called UTXO in capital letters, and the transition is done by a transaction. And then this arrow here, which is crossed out, says remove something from the UTXO set, and you have to remove the inputs from that new transaction. And you have to add, so this is a union symbol, so you have to add something. You have to add the outputs from the transaction that you added. So this is just describing what is happening under this transition. Of course, just like that, it wouldn't be complete, because you can't add any transaction to the ledger. You can't add a transaction that connects to an output that doesn't even exist, or to one that has already been taken. And that's what's written up here. So you have to say that the inputs from the transaction, they have to be a subset of the current UTXO. And also you have to say that the fee that you pay for that transaction has to be at least the minimal fee that is somehow specified by the protocol. Otherwise the transaction will be rejected. And then of course there's another very important thing here, which is that the balance, so the total amount of money of the outputs from the transaction plus the fee is the same as the balance of the inputs when you wait a second. So this is basic money conversation. So the balance of the inputs added to the UTXO has to be the same as wait a second. So the fee plus the outputs has to be the same as the UTXO when you remove the inputs. Right. Restricted to the inputs, right. Restricted to the inputs. So the inputs here, you take the UTXO set, you restrict it to the inputs that you use for the transaction, thanks. And that has to be the same as the outputs plus the fee, so that you don't create and you don't destroy money with that. And that's basically it. And then below here, you just see that you can compose those rules. And this rule here basically adds the requirement that you have to add witnesses, you have to add signatures when you want to spend any of those unspent transaction outputs. So can I get a second show of hands who's familiar and competent with this notation now? Better now? Okay. So the point I was going to make with this show of hands is that if you sit down with somebody who basically is listening to that, then you can really, it's not that complicated. It's just very basic mathematics, and this is in particular something that you can train the researchers to understand, so that they have understood their paper, and if they can also understand this notation, then they can confirm that this is indeed what they wanted to express in their paper. And you can also show that to product management, and they can also say, okay, yes, this is what we want, and we actually do this. So we have sessions where we go over those formal specifications, and then basically get everybody to agree that this is indeed capturing the intent of the paper. Yeah.
I have a short question to this, but the quality of peer reviews, it's a function of the quality of those reviewers, actually, right? So
yes, but the nice thing is, it's objective. So if you are not convinced that we're doing this correctly, you can go ahead, you can read the paper, you can read the formal specifications, or you could hire somebody, some consultants, and let them do it. It's objective in that way. It's not just trusting people to do the right implementation. It is trusting that the people who have looked at the specification and the paper have done it correctly, and if you don't trust it, you can just pay anybody to do another review of that. And you don't have to pay anybody to do another competing implementation or something like that. Or do some complicated code review where you have all the details that you have in any implementation. The nice thing here is all these details that you have when you look at actual code, they're not there. It is really concise. It fits on one page. So this is adding a new transaction to the ledger. It just fits, in 3 lines. 2 lines. This is the caption. I mean, it is, and so it is not infeasible to get a third party to do the same review and check that. And that's the difference. Mm-hmm.
How does it work with the fees? Like the fees you pay for the transaction?
So the fees basically, there is this one rule here that says you have to pay enough fees in order to be accepted. So this minimal fee is something that depends on the transaction, so larger transactions are more costly. And it also depends on these constants of the protocol that are here basically in the environment. So this thing to the left of this sign here, that's called the environment. And so this determines the minimum fee that you have to pay for a transaction. And this predicate here basically ensures that you have paid enough fees to cover the minimum fee, otherwise your transaction will not be added to the ledger.
And who's getting the fees
That's a whole other thing. So yeah, the incentive structure is basically like that over an epoch, you collect all the fees in the system and then you redistribute them amongst all the slot leaders. And the reason we're doing it like that, and not just giving them to the person just creating the block where the transaction ends up in, is that if you did that, you would incentivize the slot leaders to work against each other and try to, if there's, for instance, a block with many transactions in there, then you could try to censor that and enter those transactions yourself. And we don't want that, so that's why we have this more collaborative incentive structure.
So these specifications are for any UTXO-based system, not necessarily, it can be say Bitcoin kind of specification.
Yeah, I mean, you can write those kind of specifications for other systems as well. You can do that for account-based as well. It's just, so this is a fairly simple rule that I think, yeah, I'm going to explain. Yeah. Right.
Another
Yeah.
question. Who's issuing the fees? I mean, the money to pay the fees must be issued somewhere.
Yeah, when you create a new transaction, you use inputs. So you use unspent transaction outputs as inputs to the transaction, and those carry some money. And you have to control those. You have to have the keys that allow you to spend them. And so then basically, once you have the inputs to the transaction, you have a pool of money, and then you can distribute those amongst the outputs that you want to create. So sending that to other addresses, and the fee. So you have to have enough money just to pay the fee and the outputs. Mm-hmm.
You mentioned the proof of stake, if it's based on how much stake one has, is that information stored somewhere away in the system which nobody can access? Do you need to protect that information? Or
It's publicly, I mean, as soon as you see the blockchain, you have that information. It's visible on the chain.
So at every stage you keep checking how much each person has, and you, in each epoch you allocate based on that?
Yeah, I mean, you check this once per epoch. You take the snapshot of the stake distribution. And the stake distribution is something that you can update with each transaction, basically, because you see that so how this works internally is that each address is associated with a stake key that is used to participate in the protocol. And then you see how funds move from address to address, so the stake distribution changes. And then you make the snapshot once per epoch and use that for the next epoch.
Sorry about that. Then, just given the randomness of this process, isn't it possible that this diverges in the sense that somebody who already, if they're not even stakes already, somebody who has a high stake ends up getting higher and higher stakes because of statistically chance that the allocation is based on how much stake he has, it keeps getting higher and higher?
Because they get rewards, or?
No, because since I have high stake compared to you,
yeah.
I
You will
get
get more
higher chance
blocks,
for block
yeah.
additions.
Yeah.
That gives me more chance to increase my stake.
By the rewards, yeah. But then again, you will want to spend probably some money at some point. I mean, you don't want to just let it sit there. I mean, if you participate in the protocol in order to make money from the rewards, then at some point you'll probably spend them. So, okay. Any more questions at that stage, or? Okay, then I'll just continue. So now we've basically covered this one, that we have the formal specs that the researchers, product management, and people in the formal methods group can agree that they capture the intent of the paper. The next thing is then getting an executable specification. And the nice thing is that in Haskell we can have this translation be nearly verbatim. So if you look at that, you have above here is again the rule from two slides slides in the past. And below here is that same rule expressed in Haskell. And if you just compare, this is the thing that it should come from the UTXO, and then here you have the mathematical subset operator, here you have the set operation, set dot is subset of, but it's basically verbatim. So this is something that you can nicely check with peer review. And again, if you don't trust the peer review, you can just go ahead and put them side by side and do it yourself. And then the only thing that we add here is basically markers that tell us that if some of those preconditions is not met, then in those executable specifications, we want to see which one wasn't met, because we use this also for testing, and then when we deliberately create an invalid transaction, we want to see that it was for the right reason, so we add these markers here. But apart from that, it's really just a verbatim translation.
So what is that format? Or so the bottom piece.
Yeah.
What is that format? This is not Haskell.
This is Haskell code. Yeah.
It's Haskell code.
Yeah. So it's basically it says that this rule here, that's a data type that has a list of predicates and then a transition. And so you have the list of predicates, that's everything above that line, and then you have the actual transition. That's below there. So that's a custom data type that we defined in order to write those specifications. And this is just this is Haskell syntax in a framework that we've developed within the group, expressing this rule. And then the nice thing is that, as I said, it's nearly a verbatim translation. And at that point, the compiler can check that everything is consistent, and you can also apply those transitions to a model of your system. And so that's basically that step. And then the last step that we have to assure is that the actual implementation matches the executable specification. So how can we do that? So what we can do once we have the real implementation and the formal specification is that we can do a state transition. So we have some state of the ledger, and then we get a new transaction, for instance, and we apply that to the ledger state, and then that ledger makes a transaction. So basically you can think of this axis here as time, and then the state of the real implementation does some transition. Then you have a beginning state and an ending state. You can do the same thing with the executable specification. So the state, of course, of the executable specification will be much simpler, because it doesn't care about stuff that's on disk, it does everything in memory. It doesn't care about performance, so it can do things very straightforwardly. And so the state of the executable specification will be much simpler, but it will contain the essence of the state of the real implementation. It will contain the distribution of funds in the ledger, because that's what it specifies. So you can do the same, basically you can do the same transition from a state that corresponds to the beginning state of the real implementation to a state that corresponds to that in the executable specification. You can make a transition of that using basically the same transaction, but with some details stripped away that are not essential for the ledger. And then you can do the same transition. And you can also have a mapping from here to here. Whenever you have a state of the real implementation, you can basically strip away the details and get a state for the executable specification, a more abstract thing. And you can do that for the beginning state and for the ending state. And then you can check whether, if you go like this, you perform the transition in the real system and then you abstract away, or you go abstracting away first and then doing the transition with the executable specification, you can check whether that gives you the same result. And that's a very nice check. And so in that way you can basically check that if you ignore all the details that are not there in the executable specification, if you ignore those, whether those two are equivalent. And you can do that not just for hand-picked simple beginning states and transitions, but you can basically write generators that generate you valid or invalid states of the ledger and valid or invalid, valid states of the ledger, and then transitions that could be valid or invalid given that state. And then you can perform those in series, and then you can basically randomly generate lots of beginning states, lots of transitions, and then check whether this is indeed the same. And then of course you have to make sure that those generators are written well, that they cover all the interesting cases. But there are techniques for basically looking at everything at all the states that such a generator creates, and then making sure that everything that you would have written in the unit test are covered. And then you can get a very strong guarantee that this indeed is equivalent, the executable specification and the real implementation. And with that, you then have this complete chain from the scientific paper, which is peer-reviewed, to the formal specifications, which basically are written in a way that can be understood by all the stakeholders that are involved, by the researchers, by product management, and by the engineers. You have the executable specification. That translation can be checked by just looking at it verbatim. And then you have this property-based randomized testing between the executable specification and the implementation. And with that, you don't yet have proof that would be more costly and would take more time. But you have a chain of pretty strong evidence and objective evidence that links the intention in the paper with the result of the actually working code. So that was the second part of my talk. I don't know, do I have, how much more time do I have? Did this take too long? Are you still in the mood for more? Okay, then I'll tell you a bit about the smart contract languages that we have in Cardano, or that we are adding to Cardano at the moment. And the first one is Plutus, which is a full-stack functional language for smart contracts on Cardano. And so, who of you has used functional programming in the past? Okay, a few, yeah. So the nice thing about functional programming is that you don't just use any kind of functions, you use pure functions which don't have side effects. So whenever you apply one function to the same result twice, you always get the same thing back, and there's nothing else. And once you have side effects, you have them explicitly tracked in the type system. But as long as you handle pure functions, it's very nice that you can do this local reasoning, because the behavior of the function doesn't depend on any shared mutable state that's hidden somewhere or anything like that. So it's very nice for local reasoning and also for testing things in isolation. And this allows you to build up larger systems, and either systems like Cardano itself, or also smart contracts from building blocks that you can reason about and test in isolation. And then we also use Haskell, which has a strong type system, which basically makes sure that all the plumbing is correct and you don't screw up there. Now, the thing that you can do when you want to use a functional language on a blockchain, I mean, the languages that you have, like Solidity, they're not functional, so you can't use them. So you could invent a new one, but then, of course, this would be a lot of work. You don't have to only invent the language itself, that's the thing that's rather fun, but you also have to make sure that enough libraries are there, that you have compilers and tooling, that you have a community, that you have learning material and all of that. So what we did for Plutus is that we built upon an existing language that has all of that, which is Haskell, which we're also using for developing the system itself. And yeah, so Plutus is basically built upon Haskell, and then it has a small subset of Haskell that can be compiled and added to transactions on the blockchain. And in order to have this in an expressive way, we use something that's called the extended UTXO. So if you look at Bitcoin scripts, they're basically a two-component thing where you have a validator script that basically tells you whether you can spend some input, and then when you want to spend it, you have to add a second script, which is the redeemer script, and then you check whether the validator applied to the redeemer gives you true. And with that you can do some things, but the disadvantage is that you can't do anything that depends on anything else, anything on the value, on the state of some contract. You can't have contracts that keep some state because this is a stateless thing. Now what we did for Cardano is add some additional components to that. So each UTXO entry has, in addition to the value that is in there and potentially the validator script, you also can add a second script that can contain some data. And in that way, basically, and then you also, when you check whether the validator gives the right result, you don't only depend on that redeemer script, but you can also depend on that data, which is in the value that you want to use in the UTXO entry. And you can also depend on the overall transaction. And so it's much richer. So you can basically thread some state through the evolution of a smart contract by putting it in this data script. And the nice thing about that is that it's still just a pure script execution. So you have this script, which is some piece of code. You have the data, which is some piece of code, and the redeemer, which is some piece of code. You have the value. And whenever you apply the validator to those same values, you will always get the same result. And this is nice because you can test your smart contracts off-chain before submitting them, because some things that often happen in Ethereum is that you basically submit some transaction with a script to the chain, but then you run out of gas. You didn't put enough gas in there because you didn't know how much it would cost eventually, and so your money is lost and you can't do anything about that. But here you can actually test the execution of that validator script off-chain, and then you can see, okay, this will cost me that much, and then you can basically make sure before doing it actually on the chain that this will succeed. So this is rather nice. Another thing that's nice in Plutus, that's nicely solved there, is the thing of having things, when you want to do a smart contract, then you have one part that is actually running on-chain, so that's what you would write in Solidity and Ethereum. But then to accompany that and actually interact with your wallet, you would also have to write a lot of JavaScript code. And those two pieces of code, they have to touch the same thing, so they have to be kept in sync. You have to combine them in some rather ad hoc way, and it's not really fun, and it's also very brittle. So if you change your smart contract on the on-chain side, but you forget to make the appropriate change on the off-chain side, then stuff breaks. And you also don't have a strong type system here that ensures that stuff doesn't break, and it's brittle and it's inconvenient and it's not that good. So, but what the people designing Plutus language did is that they recognized that that's something that's actually handled in programming language theory. It's called a two-stage programming model, where you basically have a host language modifying another program in a second language. So if you write a Plutus smart contract, then you basically have the off-chain code written in Haskell, and then within that same program, you have some code that is written in Plutus TX, which is basically a subset of Haskell, and all that is then handled by the same compiler. This on-chain code is extracted and compiled down to something that can be put into transactions. But because it's done by the same compiler and it's using the same types here and there, and it's in the same source file, it's much less brittle. If you screw something up here, then the type checker will complain. It will tell you, okay, you've changed the types here but not here. You need to do that, otherwise I can't even compile it. And yeah, even less run it or commit it to the chain. So that's how it's handled in Plutus. Plutus right now is not yet integrated on Cardano, but what we have for you to play around is the Plutus Playground, where you can develop and test smart contracts, and you can test that on something that's called the mock chain, which basically simulates all the ledger rules from Cardano, but doesn't run on a blockchain, but just runs locally. So that you can already start developing your smart contracts, and then you can see how they evolve, you can test them locally. And of course, you can also then, once we're at the stage where Plutus is integrated, you can test them on the mock chain before you submit them actually to the chain. So that was what I wanted to say about Plutus, which is basically a full-fledged general-purpose programming language that can be executed on the Cardano, or that will be able to be executed on the Cardano blockchain. Another thing that I wanted to tell you about is Marlow, which is not a general-purpose language, but a specialized language, a domain-specific language for financial contracts. Because the thing is, programming in a general-purpose language is something that programmers do, but it's not something that financial experts do. They're not trained to do that. So if you want to write smart contracts that express financial contracts, then it's a good idea to use a language that is more familiar to domain experts, that's more amenable to domain experts, because it doesn't have all these things that you have in a general purpose language, but that are not really relevant for financial contracts. You want to focus on the essence and have a language that is small and that basically can capture the intent of financial contracts, but not too powerful, because too powerful also means too difficult to learn and too inconvenient, and you don't want to restrict yourself to having people who are both trained in financial contracts and general purpose programming. So you want to have a language that is suitable for domain experts. That's basically the gist. And so just to show you an example of how that works, let's look at a very simple example, which is an escrow contract. If you have somebody wanting to buy something from a buyer, but they don't trust each other, then as long as you have a third person that both of them trust, you can do stuff like that. Alice gives the money to Carol, and then afterwards Bob gives the cat to Alice, and then tells Carol about that, and then he gets the money. And otherwise, in the other case where just Alice gives the money to Carol, Bob doesn't give the cat and nothing happens, then at some point Alice can get back to Carol and get her money back. So that's a rather simple thing, and it's a useful thing. And in Marlowe, you can express it like this. You have basically this condition here. When you either have the condition that you should get a refund, or you should pay out the money, then you do a choice that if the result is that you should pay the money, then Alice pays the money, and otherwise she gets the money back. And so that's basically in quite simple. So this is a language that really just expresses the content of this escrow contract, and it's something that you can it's not meant to express general purpose programs. It's meant to express just these kind of contracts. Of course, if you just do it like that, then you wouldn't really have a decision if Bob just waits and doesn't do anything for a certain amount of time. So what you want to do there is to introduce some timeouts. So you say, okay, I want to buy this cat and I want to have it like within a week, and then if nothing happens for a whole week, then Alice gets the money back, and the thing is considered to be failed. And in order for also making it possible for the buyer to do a commitment, you also add some constructs like you want to be able to commit some money, and then once this is executed, Alice has basically 10 rounds of time until she should get that money down, and then it's committed until round 100, and then this inner thing is carried out. So in that way you can basically make sure that contracts get enforceable. So once Alice has committed to that, I mean, nobody can force her to commit that money, but once she has committed to that, she has a finite amount of time to do that. Then you have a finite amount of time in which this contract can run. And also, if she chooses not to commit that money, then after 10 rounds, basically time passes. Because the thing that you want to prevent in these smart contracts is that people just walk away and don't do anything, and then the program just halts, and the money that's in there, it gets locked. So in Marlowe, you have these constructs like timeouts, where you say, okay, if nothing happens after a certain amount of time, then just you do whatever is appropriate at that amount, so Alice gets the money back. Or in the case that Alice doesn't even get the money down after 10 rounds, you just continue doing nothing. And then also, if she committed that money and after 100 rounds nothing happened, then she can go and reclaim the money again. And now the nice thing about that, I mean, this is already rather nice because it's a language that's close to the domain of financial contracts. But you can also do this in a way that is somehow still far away from text-based programming, where you have these kind of blocks, this commit cache block, which says, okay, you have an identity, you have these different fields here, you have Alice, you have the number of rounds, you have the amount of ADA that should be committed, so the amount of currency that should be committed, and then those timeouts, and then you can insert other blocks in there, and then basically those shapes of the blocks, they act like a type system in restraining which blocks can be put into which holes. And so this is then something where you can basically look at the structure, and you're not required to write actual programs, and then you can combine and compose those. And then we have
is there a relation to Marlowe and Plutus, or are they independent?
Yes. So Marlowe gets compiled. They get compiled to the same, to Plutus core, which is basically the underlying language. And you can also, if you wanted to, so because so I haven't put the slides of that in here, but because Marlowe itself is also a domain-specific language embedded in Haskell, you could also take Marlowe contracts and then basically take constructs from Haskell to enrich them, but you're not forced to do that. You could just write them in Marlowe, but you could also use some constructs from Haskell that you feel comfortable with. If you've written those things for a certain amount of time and then look a bit into Haskell, you could also enrich that with Haskell, and that would still be embedded Marlowe contracts.
Who's the target audience for Plutus?
People who want to write smart contract applications. So if you want to do more than just financial contracts, if you want to do something like, I don't know, CryptoKitties or so, then you could do that in Plutus, and you wouldn't have to do this this manual ad hoc two-stage thing where you have Solidity and JavaScript. You would have a strong type checker aiding you, and yeah, you could do that in a way where you can do local reasoning. We have all the benefits that people use Haskell for, but you can do something on blockchain with it.
So the project made the decision to make Plutus Core like a general programming language. Right?
Yeah.
Because sometimes it's actually,
And
in the case of Marvel, it's actually beneficial to restrict things, not to make it.
Yeah. I mean, so as long as you stay within Marvel, you're restricted. You can, if you choose, you can also use general Haskell constructs, and then I mean the underlying thing, Plutus Core, that's actually it's a very old and very established and very simple language. So it's a system F omega. So that's.
So when you say it's old and established, what are you
from the programming language community. So it's
from which community?
The programming language community. So it's a thing that's been used in programming language theory for decades, and so that means that it's quite stable and it won't change tomorrow. So it's because the thing is, if the thing that's actually on the chain, that's something that you don't want to change that. I mean, if you want to make additions to the language on the surface, if you want to add syntactical sugar or something like that, then that's fine. But you don't want to change the actual representation on the chain too much.
So you specifically chose the word syntactical sugar. So actually, the VM that you have there is Haskell syntactical sugar over that VM that is really executing the contract, or how does it work?
So if you look at this this here, then you basically. So I mean, up here you have general Haskell, and then down here you have Plutus TX, and that is then compiled down to this very simple language, and that's what's committed to the chain then.
And which is that specific, that kind of?
This is Plutus Core, which is basically the system FM.
Plutus Core is kind of the VM that's going to be doing the execution.
Yeah. Then we have an interpreter for Plutus Core, which we then basically then the next step is to add that interpreter to Cardano itself. So it's basically at this stage a Haskell library that can execute this kind of code. And so because it's a Haskell library, it's quite straightforward to add it to the Haskell implementation of Cardano. And we also the other, if you wanted to use that with another system that's not written in Haskell, so for instance the Rust implementation of Cardano, then we have a server that basically has a REST API where you can send it scripts and values, and then it can give you that decision of whether it's...
that was my follow-up question, because you didn't talk about Rust.
So there the plan of integrating that is with this REST server. Where you have a server written in Haskell that basically can execute Plutus scripts, and then the Rust code can send requests to that, sending it the code that it saw on the chain, and then getting back the answer from the server who ran the actual script. Yes, this is. And server can also
side by side.
They can be on the same node and everything. It's just when I say server, it's just a standalone Haskell program.
Out of process.
Just making sure I understand this properly. So Plutus Core it's not a new thing. It uses something that's already.
I mean, the theory behind it is well established. So when they thought about which language should we use, then they looked to programming language and established things and said, okay, this is basically this is basically the language that we want to use, and now we're writing an interpreter for that, and we're calling it Plutus Core, and that's that. And maybe there are some additions to that. I'm not too sure about that because bottom line is just they chose something that's very well established, and that's not going to change.
So Philipp Kant is working this, right?
Yeah.
Do you know what he chose then?
System F omega is what he chose, but
System F omega.
Yeah.
So if I'm keeping that, maybe I can catch you up later. But so now this is running out of process, and the node Rust, like the Rust node, is going to handle all the communication databases and everything. So how the state is communicated between like the node, or you keep like two.
So when you look at the at the execution of the Pluto script, you don't need the general state of the ledger. You only need those items here. You need the scripts, basically, the data script value and the thing from transaction. So it's rather, you don't have to send the whole ledger state all the time, because that would be excessive. You only have to send these informations, basically. And because it's a pure function application, yeah, it's something that you can do with an investable way. Yeah.
But this doesn't impose like a major block like a bottleneck. You have like,
I wouldn't.
You cannot run in parallel because you need to pass the state for each of the transactions, so you cannot like parallelize probably. And
you could also do that, but I don't think that'll be the actual bottleneck. I mean, the actual bottleneck is, I mean, the things that we're concerned about that are really the things where we are worried, or not worried, but where we have to look at the performance in order to set the parameters of, I mean, we have slot lengths of 20 seconds. Every 20 seconds there's a new block. And so the thing that we have to make sure is that we actually have the propagation of the information through the network happening fast enough, so that the blocks can get to the next slot leader in 20 seconds time. So that's the things where we expect bottlenecks. Executing the scripts, yeah, I mean that's not where I would think systems. Yeah, that's not where the real problems lie. I mean, as you said, you could also have this in parallel. You could have 5 servers running, and then if there's a lot of scripts, do that. Yeah.
You mentioned the financial language which you're building for doing this.
Yeah.
With S, for example. You also plan to use that for there's this actors, these new protocols which are happening, being implemented as smart contracts for modeling financial instruments at the base level.
Yeah. There's also this actors. I haven't mentioned that at all, but there's this actors group which basically has a taxonomy of all the financial contracts that you see, and there's work on implementing all of those in Marlow.
Would you do it with this language as well? Would you implement those with?
Yes, and we're doing that. Yeah. So that when you want to use some financial instrument, you can just pick it from the library once we're done with that. Yeah.
So I'm just a bit confused about the Web3 part in the browser. So how is that implemented with the Bluetooth TX?
Which one?
Yeah, if you put the Solidity part and the JavaScript part.
Yeah.
So how is the JavaScript part run in the browser?
Yeah, you can compile Haskell to JavaScript.
Okay, so it will generate the, okay, and it will generate like the library that you will use in your browser, but you still have to
You can write the whole front end in Haskell, and then it gets compiled to JavaScript.
If you need to change something on the front end, you need to change also the same contract.
Yeah, but I mean, as long as you only change this and not that, then and if you indeed do a change here that would require you to change that, then you will get told by the compiler, because the types will no longer match. I mean, unless it's, I mean, of course you can do logic errors still, but if you add something here and you don't add it there to the structure, to the types, then you get told. So as long as you do something where you can get away with only changing that, then you can do that. And if not, then there's a high chance that you will actually get told by the compiler that you have to do that.
And it will generate like a package and then you use it on that.
Yeah. Right, that was right. Yeah, and so for this block-based thing, we have a browser-based tool where you can develop and again simulate the smart contracts and step through to and that's what I was going to say about smart contracts, unless there's any more questions to that part. Okay, then just one slide on future developments. So the next thing that's coming on the agenda is what we're calling the Shelley release, which is about decentralization and delegation. So right now we have the system running on Orboss, but all the stake is hard-coded, delegated to a federated network that is operated by IOHK, Cardano Foundation and IOHK. And that's, I mean, so we can get some confidence in seeing how the protocol works and having everything under control and not releasing it on the first moment and just giving control to the wild and risking that something bad happens. So at the moment we're still in a position where we can closely monitor the behavior of the system, and we're running it with the Orboss protocol, but with all the stakes basically rerouted to us, so to say. So people can still spend their money, but the stake always stays with us. And so the next step is opening that up so that people get control not only of their money but also of their stake. And so that's been that turned out to be more complicated than we thought, because if you open it up so that everybody has control of their own stake, you don't really want everybody to run their own nodes, because not everybody will want that. And then if people just don't do that, you have a lot of active stakes, so the chain progress gets slower, the system becomes easier to attack with a 51% attack, and stuff like that. So what you want to do is that people delegate to people who basically run those nodes professionally, and then they get rewards and they share that with everybody else. And setting up a mechanism with how you can do that basically is secure and allows people to still control their funds, but centralizes that stake, and then also pays out the rewards automatically, because you don't want to rely on the operators of those stake pools to do that by themselves. You want to do that handled by the system. So that was quite a thing to design that, and that's the next thing that's on the line. And then afterwards, I told you that at the moment we have this Plutus library that can execute the smart contracts, and then integrating that into the Cardano system is then basically the next step. And while we're doing that, also implementing that extended UTXO way. We have these data fields in the UTXO as well. And the way that we're doing that is that we have these executable specifications for the ledger, and they're quite modular. And when we want to add a new feature, we start by just adding something to those specifications. And so we can basically add those changes at a high level of abstractions where we're not distracted by all these details. And then we can basically apply those changes to the executable specifications and the code as well, and still have then that thing where you have this chain of evidence that everything works nicely. Another nice thing that we're also planning to add are native multi-currencies. So when you look at these Ethereum things, then you can create basically your own tokens on there. But they only, if you want to send them, they live inside smart contracts. So you always, every transaction for them have to be in terms of smart contracts. With Cardano, we plan to add the ability that you can create your own currencies that live just in the ledger themselves. And so in order to create those, you would have to use a smart contract, but then once they are created, you could just send them away just like ordinary, just like ADA, which is the native currency.
And one of the problems with these with ERC20 tokens is you always have to have gas, somehow. So that would not be the case here.
Yeah, well, you would just have ordinary transactions using ordinary fees, and so that's.
But you still would need to pay your fees possibly in another currency other than the one that you issue.
Yes. So at the moment we are. I mean, in the short-term future, we will stick with all the fees being paid in ADA. And the reason for that is that the incentive structure, which is also something that I could talk about for an hour, but I won't. The incentive structure is in such a way that all the fees get pooled and then redistributed. And so if you just say, okay, I pay fees in some currency that I created, then you can't, a single producer couldn't really make the decision for the collective to include that. So that's why we're staying with ADA as the primary currency for fees, because otherwise we would need basically to have an on-chain mechanism of assigning value to something that I just created because I wanted to. And then with a native multi-currency, we'll also have non-fungible tokens. So something that's not just described by a number, but something like, I think crypto kittens is probably the most prominent example, or something representing houses and stuff like that. The next thing then is, or one of the next things is side chains. So that's the idea that you can transfer value from one chain to the other in an efficient way and in a safe way. So the idea is basically you destroy something on one chain and you get a proof that you've destroyed that to the other chain, and then you can create it there. And so via that you can basically have parallels that are, you can have chains that are in parallel, and you can get occasionally value from one chain to the other. And this will, these transactions will take some time, but you can do that. And then this will give us some way of, on the one hand, scalability, because blockchains don't really scale that well. And on the other hand, it will give us some safety properties, because we have something called a firewall property that says if you basically create money, if you have some incident where it's possible on one chain to create money, that you can't really get more money back onto the other chain than was transferred from there in the first place. So you can isolate risk, and if you add more complicated things to one chain, you can still have the main chain be safe. And it also allows you to offload some work. So if you, for instance, if you have some smart contract that gets very popular and that people want to execute a lot, then on Ethereum, if you have that, then the whole Ethereum blockchain gets blocked by that. Whereas in Cardano, once we have sidechains, you could just say, okay, we suggest that people use the smart contract on a sidechain. We make it very, very expensive on the main chain, and then people will just move to the sidechain, and the main chain can still transfer money quickly. And then finally, the big goal that you also said is that Cardano itself should be in the hands of the community, and so also the development shouldn't be restricted to just IOHK. So the thing that we're planning to have there, which is still in the research phase, is that you have these update proposals, and then people can vote basically on which updates they want to have implemented, and also which they want to have funded. So that always a small part of the monetary expungement of the fees gets just pooled into a pot called the treasury, and then people can propose to make updates to the system, and if people say yes, this is something that we want, then they can get some money from the treasury for that, and then that way we can ensure that there will be funding for updates even when IOHK moves on to other things and doesn't, is no longer the sole one, or not the sole, but what the sole implementer of Cardano.
I have a question to multi-currency.
Yeah.
So I might be impacted by my banking past, but you mentioned that the fees would be in ADA currency. What about FX risk with these fees? Yeah, because if it's a new currency, loses the value. So at a certain moment, it will be just uneconomical to pay fees if they are fixed or to you in ADA.
I mean, so if the one currency that you want to send becomes much less valuable than ADA, and then it's no longer, okay, I mean, one thing about the fees, I mean, it is possible to adjust the fee structure. And that's done basically, there are parameters that are recorded on chain. So that's how we react, or how we can react in case that ADA gets much more expensive, then we could basically lower the fees in ADA because they're meant to cover the costs in dollars, euros, whatever. So that's something that we can do. Of course, if you have something that's, I mean, and in principle, the fees should reflect the costs to store the data and such. And so if you have a currency where it's not viable to do a transaction, then I guess if it's not worth it to you, then you shouldn't do it.
Questions are sidechains also aiming at shortening the time frame, so from 20 seconds to 2 seconds for a retail sector, or
no, so that's more like, I mean, if you want to shorten the time scale, you have to make sure that the block propagation is fast enough. And so sidechains don't help you with that. They do help you if you get basically more people using the system. And then if you have basically, you can segregate that, and then you can have people using one chain or the other, and then occasionally having those transactions between chains, which will be slower than ones on a single chain, because you have to transfer that proof, and basically you can, and you have to make sure that you only transfer that proof after you make sure that no fork, that you're after basically the fork length that you should allow for. And so one thing that we're doing now, actually at the point where we, at the next update already, is shortening the slot length to 2 seconds, but at the same time changing the protocol which is called Orboss Browse, which is one of the extensions of Orboss. And there you have a thing that the slot leader schedule is no longer a one-to-one thing, where you have one leader per slot, but you have a situation where each slot leader has a private election, there's a private lottery, and then the probability of winning that depends on their stake. And so you have 0, 2, 1 or 2 slot leaders per slot. And on average, you will have only a slot leader every 10 slot lengths. So, and the thing why we're doing that is that the adversarial model of that actually incorporates or is able to deal with network delays. So if you have network delays and if you have nodes that don't get blocks fast enough in Orboss Classic, then you count those for the purpose of the security analysis as adversarial, because they're not able to adhere to the protocol, so they are enemies basically. And so the more network delays you have, or if you have your universal network delay, then the formal analysis of the security looks bad. And it's not a gradual thing, but it's either you have it in the slot or not. Whereas in Orboss Browse, it's more advanced. So you can have network delays, and then the more network delays you have, so in the model they are controlled by the adversary, so he can direct them, and the more network delays the adversary can cause, the easier it gets to attack the system, but it's a gradual thing.
Once you activate delegation, can you explain how inflation or emission would work?
Mm-hmm.
What would be the impact on data price?
I
mean, you cannot predict that.
Yeah. I mean, so activating that, okay, there's multiple things to be said about that. One thing is that it will not just be a single switch that we flip, because that again would be too risky. But we have basically this thing where we keep the old nodes operating, and we have a slider that we can turn, and then we say, okay, if we have that slider at 1, then still the old network is the sole block producer. And if we put it to 0.9, then 10% of the blocks will be created by stake pools, and the rest will be there'll be like an overlay, and then the rest of them will still. And then we can basically monitor the system health and decrease that slider until it's in the hand of stake pools completely, and then we can turn off the old nodes. And then the monetary expansion. I mean, the idea is there to have like an exponential decay of the reserves, like you have in other systems as well. I'm not sure whether we have fixed the parameters yet for that, how fast it will be. But and then the effect on price is something that we'll all see.
But initially, you want like start like the mission immediate to the delegation, but we kind of ramp up.
Yeah. I mean, the idea is to do it in such a way that the rewards will still be. I mean, the rewards will be inflated so that it'll be as if you're running a stake pool, then it'll be on average as if you were still producing all the blocks that you were supposed to produce, because we don't want to take that away from people. But just for security reasons, to have a backup in case that something goes wrong with a decentralized thing, we'll keep some level of control there, and then basically monitor the system, and then let it move let it exit the nest slowly.
And when is that planned? Or
I mean, we're currently. I mean, we did this whole formal approach that's basically a rewrite of the system that we launched initially, and so we're nearly at the point where we can deploy that, and then we're having this pipeline approach where the specifications are already ahead and have the rules for delegation in there, so it'll be an update to that system then. I don't really like to talk about timeframes too much, because it's people nail me down to that then. It's like George Martin. Any more questions? That's
Question on actual projects you are actually right now undertaking. I know you're doing a lot of training in Africa and some other regions, but actual projects, context, interesting stuff.
So there's a book on Plutus that's coming out. I think you can already pre-order it on Amazon. I think it's called the Plutus book or something. That's being written. We have Udemy courses, I think for Plutus and Marlow. Unless it might also be only for Marlow. I'm not 100% sure on that. There's courses on that. Yeah, there's the education courses. I'm not sure whether we've decided what the next one will be. I've heard something about Mongolia, but maybe that was also the course in Plutus that was being held there last week, the week before last. Yeah, there's a few collaborations with with larger entities. I'm not sure which of those are public, unfortunately, so I'm not sure what I can do about that. But yeah, so we have this we also, besides Cardano, we also have the Atala group, and they're aimed more towards these permission systems for like large stakeholders, consortia, where you don't really want a public blockchain because the overkill on performance is not what you want. And they are looking at collaborations with multiple entities, but I'm not sure which of those are public knowledge yet. So.
Any more questions? So I just have one more thing to say. The CV Labs are providing an open bar, so we can all go downstairs and have some drinks there. And I'm sure if you have some more questions, we'll all be around to answer them. So thanks very much for coming.
Thank you.